Let's go to the semiconductor once again. This map shows you how complicated is the material choice for one single application domain, that is the solar panels. You can see the history and the evolution of the material science in the last 40 years. We started with the very basic assumptions regarding the p-n junctions and semiconductors. So at first, solar panels were realized by monocrystalline silicon, polycrystalline silicon, and amorphous silicon. But year after year, researchers found new means of producing energy through different materials. So you will see that nowadays we have the thin film technology that involves very complicated compositions, like for example the so-called SiGs materials, which means copper, indium, gallium, selenide. Another possibility is that of using cadmium telluride, which is another binary compound, a little bit environmentally unfriendly. Or more recently, the so-called dye-sensitized solar cells were developed, where the concept is radically different. You have titanium dioxide in a nanostructured form that is used to separate the excitonic couple. There is a dye that is a molecule which is converting directly the energy associated to the electromagnetic wave into the hole and an electron, and you have a layered structure, which is also, by the way, transparent, so gives you new means of using the solar panels in windows, for example. Very recently, they started to study perovskites as interesting materials for the energy conversion, and the efficiencies which have been reached in the last years are well above 10%, meaning that we have many technologies to choose. And regarding the old systems, so for example the monocrystalline, polycrystalline, amorphous silicon, the efficiency ever increased, so we reached very good levels. We may also think of adding layer to layer and concentrating the light to increase the efficiency furthermore. So our best examples of multi-cells, like 3 or 4 junction cells, are able to go beyond the 40% efficiency in conversion, which is huge. So anyway, the point is that material science is progressing thanks to nanotechnology studies, and new materials add to the list of possible choices to realize the same basic function, in this case energy conversion from electromagnetic waves. Let's go to the substrates once again. I want to show you how it is possible to differentiate between the structure of the material. We usually address zero-dimensional systems as small nanoparticles. One-dimensional systems as nanowires or nanorods. So in that case we have just one single dimension, which is higher than the nanoscale 1, which is the section of the rod or of the wire. We have two-dimensional systems, which are the thin films. So layered structures, flexible or rigid, depending on the substrate. And then we have mixture of one of those 3 possibilities. So for example, we have nanocomposites which are 0-3, meaning that we have a zero-dimensional filler, for example nanoparticles of zinc oxide, which are dispersed in a 3-dimensional bulky part, for example a polymeric material. We have 1-3 coordinated composite materials, meaning that we may have a dispersion of carbon nanotubes, which are 1-dimensional, into a interconnected 3-dimensional matrix, which is 3-coordinated. We may think of having 2-3 coordinated composites, meaning that we have 2-dimensional sheets like those of graphene dispersed into an interconnected 3-dimensional matrix. We may also think of having a 3-3 coordinated composite material, where we have interpenetrated and fully connected bulk components realized by 2 non-miscible materials. An example of this is the bulk heterojunction solar cell, where you have a polymeric material that has a behavior like a semiconductor n-doped, and another one that has the p-doped behavior. And they are mixed in such a way that are fully interpenetrated. And it is possible to increase in this way the surface, the contact area between the two materials, while preserving the simplicity in handling and fabrication, because it's just one single composite. What about now the structure of the material and the different scales at which a material is structured? So let me go through this slide, which was taken from the Ashkeland book. This example is very simple and very basic. It starts from an engine block, okay? For example, you may think of a diesel engine, which is realized by cast iron. So this is a macroscopic object. You may think of all the issues that there are behind the realization of an engine block, all the production processes that you may develop to obtain and match perfectly your requirements. In particular, the melting and the casting of the iron and the eventual mechanical working of certain parts of it. And for example, the hardening processes that could be used to increase the resistance to wear of certain parts which are exposed to the piston movement. All those issues are so-called macroscopic issues. Then let's go one step further. So, for example, to the micro scale, we may notice that every material is composed by crystalline grains, where the orientation of the atoms is absolutely coherent. Otherwise, outside this coherence zone, there is the so-called grain boundary, where the atoms are disordered and in a glassy structure. A macroscopic structure normally has a polycrystalline definition, meaning that we have many different grains, each one is oriented in a certain way. Other objects, like for example the monocrystalline silicon cylinders, have one single very big macroscopic grain. So this is a very particular case. If you have a single crystal, you have also anisotropy in its properties, because depending on the direction on which you stress or you analyze the properties of the material, you will find different numbers. While if you have a polycrystalline structure, since the orientation of the grains usually is random, the properties are isotropic, so you don't find any difference depending on the direction of your characterization tool. There are other opportunities. For example, if you have a polycrystalline material and you process it in such a way to induce a preferential orientation of the grains, then you will end up with an anisotropy in its properties. Such an example is that of the transformers. The transformers have an iron steel, silicon steel board that is grain oriented in order to have better permeability of the magnetic flux line according to a certain direction. So the working process allows you, to orient the grains and recrystallize a little bit the material in such a way that you will find mostly grains which have the same anisotropy axis. Let's go one step down. So if you go in between the micrometers and the nanometers, you will find more interesting phenomena. For example, the grain boundaries, as I told you, and you will start to see that there may be certain nanoscaled precipitates, in particular into the cast iron structure. Those precipitates may be even graphite flakes or intermetallic compounds, in particular cementite, which is Fe3C compound. So it's a perfect alloy that has the exact composition Fe3C, and it has a huge mechanical hardness, but also it's very brittle. You may try to structure those inclusions, so give those inclusions a preferential crystalline structure and direction. And if you're able to do this, you will achieve another key, another means to increase the mechanical properties, for example, along a certain direction. And if you go to the atomic scale, you will see that the grains are composed by single atoms. So by substituting those atoms, for example, with another compound, another element, you could induce other properties, like a resistance to wear or like self-lubricating properties. So depending on what you do and at what scale, you achieve different results. Let's go back to the macro scale structure. So you see this picture is a TEM image showing you all the parallel planes in a crystal. So it's a cementite lamella. In this other example, I wanted to show you how it is possible from the microstructure to go back to the mechanical properties, in particular to the fatigue. Fatigue means that you have a cyclic stress that is acting on your structure. Okay, so you have like a sinusoidal mechanical stimulus, and your structure should resist, so you should withstand this stimulus for a long time. What happens normally is that if you have a failure and you watch under the electronic microscope at the fracture surface, you are able to understand what happened and why the structure failed and how it is possible to reduce the probability of going through such a failure. You see that the fracture is divided into two different surfaces. One which is a little bit even and another one which is very opaque and has clear directions. So what happens is that normally the fatigue fracture starts from the surface of the material. When there is a flow in the surface, so the surface is not perfectly smooth and even, the stress propagates from that flow, and cyclically the crack is further expanded until a point where you have reached the maximum strength of the material, and it breaks dramatically in a fast way, in a brittle fracture, so-called, and you can clearly see the difference between the two regimes of the propagation of the fracture. Let's go now to the yield strength. So the crystalline structure is influencing all the mechanical properties. In particular, if you have very big grains in a material, in a macroscopic object, you take the risk to have also a very brittle material, because big grains also mean that you have not a perfectly homogeneous structure. If you are able to reduce the size of the grains, you are also increasing certain kind of properties, in particular its ductility. Because when you apply a mechanical stress to the material, all the grains which are small enough and have a huge amount of grain boundaries between them are easily flowing at the same speed of your application of the mechanical stress. And this is important if you want to prepare a structure that is also plastically deformable, not only elastic. Okay? So depending on your needs, you should carefully select the crystalline structure. Let's go to the precipitates and to nanoscale phenomena. On the left side, you see what happens when you submit a material to a plastic deformation for a long time. This is the so-called dislocation forest. Dislocations are nanoscopic or nanometric defects in the ordering of the atoms. You may think about a roof which has tiles. If the tiles are perfectly aligned, there is no flow in it. But if you add another row of tiles and you arrange the neighboring tiles in order to correct this, you will have one single point where this dislocation starts, which is something like a failure point, a failure starting point for all the mechanical deformations. So from that point, some dislocation, some movements in the atoms will be generated when you submit the material to a mechanical stress. And you can see actually them through the transmission electron microscope as black parts where the atoms are disordered. And you can still keep deforming the material and submitting it to a mechanical stress until the density of those defects is high enough to make it so brittle that it breaks. An example is when you have a copper wire or an iron wire and you want to break it. So you start to mechanically move it up and down, up and down, up and down. It releases a lot of heat, so if you touch it in the bending point, it can be very hot because it is releasing thermal energy after all the accumulation of the dislocations. And when you reach the critical density of dislocations, it breaks. It becomes brittle because you cannot further generate defects in the structure. There is a way to recover this structure and bring it back to the flawless crystalline lattice. And this way is called recovery. Recovery goes through a thermal treatment. So if you want to have a material which is very ductile and very plastically deformable, you should submit that material to a thermal treatment in an oven. Normally this is done at a temperature which is 2/3 with respect to the melting temperature of the material. And you completely cancel all the dislocations until a certain level. So you always will have a minimum number of dislocations or defects in the lattice, which is connected to thermodynamics. So you cannot go below this limit.